Hi everybody. In this video lesson, we're going to talk about wave-particle duality. So not only of light, but also of other particles as well. Before I forget, I want to briefly mention too that there's lots of great useful videos I've posted. Not that I made, but from places like Crash Course Physics and Nova that go into the quantum mechanics in a bit more detail and have some really great visuals and illustrate some of the things we're going to talk about. So I definitely would encourage that you give some of those a watch. Most of them are on the shorter side, less than 10 minutes. But I know that one Nova episode I posted is about 45 minutes long, but it's very fascinating. All right, let's get started. We're going to start by talking about the Compton effect. So right now, we've kind of established that we can think of light as both a wave and a particle, and that particle we call a photon. So in 1923, Compton directed some high-energy X-rays at a very thin metal foil. So this experiment was pretty similar to the photoelectric effect, but instead of visible light, we were using like X-rays, which are very high frequency, high energy light. So I'm going to draw a little visual of this. So we have some thin piece of foil. And we have high energy. And again, that just means high frequency X-rays. And to illustrate their high frequency, small wavelength, let us do that, coming this way. And what he found was when they struck the foil, what happened was they got emitted electrons. So kind of like the photoelectric effect. So you had an electron with some kinetic energy, and you also had, because you had an electron with that energy, but then it came off some lower energy X-rays, and I'm going to indicate that they're lower energy with a lot longer wavelength and a lower frequency. So lower energy lower frequency X-rays. And this kind of gave credence more to the particle theory of light, because this is like a collision where we had some high energy, and then afterwards we have some lower energy, and that difference in energy was made up by the electron with some kinetic energy. And if we can think of it as a collision, maybe, and this was Compton's kind of stroke of brilliance, if this is a collision with kinetic energy conserved, which it was, he kind of showed via the energies of the lower energy and electron matching the original higher energy. But if that kinetic energy was conserved, what of momentum too? So again, his experiment gave more evidence for the photon theory of light we've already talked about. That light travels in discrete bundles of energy, photons. Those photons have an energy of hf. F is the frequency of that light. And he showed that, unlike the wave theory of light, when shining light on a metal, it was like the photons of light were undergoing a little mini collision with the metal and the electron, freeing the electron with some energy, and then the lower energy light being produced. So we're just going to talk about this collision in terms of kinetic energy first. So we had some energy of the photon, and so we've used the Greek letter gamma. We use gamma for like gamma radiation, or basically light. So here we have a photon with high energy. And this is just putting into just a little bit of an equation, what we just talked about earlier. And we got energy of a photon, and I'll put prime. And I'm just indicating that's a photon with another photon with just lower energy. plus EK. And this is the electron kinetic energy. And so putting that into plugging what we know, we had the energy of the photon, HF, equals the energy of the lower energy photon, which would be H, I'll say F prime, plus 1/2 mv squared, the kinetic energy of the electron. And so if he knew what the frequency of X-rays he was using before, and he can measure what kind of lower energy X-rays were coming off and measure the speeds of the electrons. And now we're into the 1900s, so it's a bit easier to do that. Not easy, but easier than it was in the 1800s. He could actually show that kinetic energy was conserved, and he did. So Compton's experiment observed, hey, this held, and kinetic energy was conserved. It was like an elastic collision. Again, and if it's undergoing collision and it's kinetic energy is conserved, this is kind of showing, hey, this photon, this light is a particle. It's undergoing a collision. But if kinetic energy was conserved, what about momentum? But how can momentum be conserved? Like if light, a photon, has no mass, no rest mass, how can it have momentum? Well, the key was Einstein's mass energy equivalence equals mc squared. I think we're going to do that derivation on the next slide. Yes, we're going to do that derivation right now. So check this out, guys. This is so cool. So we're going to start with our just momentum, P equals mv, right? And I'm just going to go right to left because on your sheet, we're at the bottom of your page, I think, and so you don't have a lot of room vertically. So let's think of a photon. What's a photon's speed? Well, it's traveling at the speed of light, right? So that's not a big deal. For V, we're going to plug in C. What about for M? But remember, guys, mass and energy are equivalent, related by E equals mc squared. So I can replace M with E over C squared and get E over C. The momentum of a photon is its energy divided by the speed of light, and we know that's equal to HF, the energy, over C. So all these equations are equivalent. Momentum is energy over the speed of light, and this is for photon momentum, which is HF over C. And if we replace C with the wave equation, C equals F lambda, then you get a different equation just in terms of lambda. You get a very tidy, cool equation. The momentum of a photon is given by Planck's constant divided by the wavelength. Pretty cool. So photons have momentum too. And you get an equation for that momentum by using Einstein's equals mc squared. That's pretty awesome. And so to see if this is true, Compton went back and looked at the momentum. So we had some X-rays with certain momentum, h over lambda. And then we had this lower energy X-ray going that way. And its momentum would be h over lambda prime, some new wavelength. And then the kinetic, the electron had some momentum down this way. And he could check out, was momentum conserved? So this was the momentum of the original X-ray. And you can find the momentum for the lower energy X-ray and the momentum of the electron. And like momentum was conserved too. So pretty fascinating stuff. So again, Compton's work just further reinforced that light is a particle. It's a photon. We can think of it as both wave and particle. And he won a Nobel Prize for his work. One brief last note here that's on your note. Light intensity is measured by the number of photons emitted from a source. So high intensity light that is really bright, doesn't have more energy. It actually has more momentum because there's more photons, so more momentum. But each of those individual photons would have the same energy because they have the same frequency. So I think you have a few Compton effect momentum of a photon questions mixed in there. But I'm going to tie in just in one lesson here. We're going to talk about wave-particle duality as well. So we've hopefully established now you're quite comfortable with the fact that light, we can think of it as a both particle and a wave. But wave-particle duality says that, not just light, but all particles exhibit properties of both waves and particles. And the most classic way that this is illustrated, and it's in at least 2 of the videos I've posted on Brightspace, was that, let's put this as like a little example. Just like in Young's double slit experiment, we saw that light diffracted and produced interference patterns. Electrons were observed to diffract through a double slit. So that was pretty fascinating at the time. Like, we've already established that Young's double slit experiment showed us that light diffracts, and we could predict what those patterns look like. But actually, if we did it with firing an electron beam, like actual physical particles and not light, that you actually got a diffraction grading pattern for electrons as well. So the electrons were being deflected or diffracted when they were being shone through a double slit. And if electrons are diffracting, then we can think of electrons as a wave too. And you can think of a bowling ball as a wave, you and me as a wave. All of us have an associated wavelength with us. And we're going to talk about that in just a moment. So we have already established wave-particle duality for photons. So although light has no rest mass, it does have momentum. Just as we talked about with the photoelectric effect, with the Compton effect, that a photon of light can behave like a particle. It has momentum, undergoes collisions, dislodged electrons, kinetic energy and momentum were conserved. And we've already established the momentum of a photon is found by P equals H, its energy over C. And we had various variations of that earlier on. Right here, right? E over C or HF over C or H over lambda. But Louis Victor de Broglie, again, he was the first one to kind of propose that, if light had properties of both a wave and particle, then other particles should too. And using the momentum equation that for light derived by Einstein above, and I kind of already teased this with you guys. You can show that the associated wavelength of a particle that has a certain momentum is the de Broglie wavelength. So I don't think you guys really need to do the derivation. It kind of comes from if P equals H over lambda equals H over P. So we started with, fun cursor here, P equals H over lambda, and that held for a photon. He rearranged that for lambda and argued that, well, if I actually had some actual object with mass and I use the same equation, I should also be able to see this wavelength. And so, as I mentioned, electrons were observed to have this property and diffract. But I might just do a quick example with you right now. Yeah, let's do a quick example. It won't take a lot of space. But let's find the de Broglie wavelength for I don't know, how big's a bowling ball? 5 kilograms perhaps? 5 kilogram bowling ball. Let's say we roll it down the lane, and I'm not sure, maybe at 10 meters per second. Let's find the de Broglie wavelength of this bowling ball. It has one. Let's check out its length. Because I don't know about you guys, but when you're at the bowling alley and you're throwing a bowling ball down the aisle, when it gets down to the end and passes through the little gap, you don't see a bowling ball deflecting and diffracting left and right. You know what I mean? If you were to take a bunch of bowling balls in a hallway and shoot them through a door, you're not going to see diffraction happening. And here's why. The de Broglie wavelength would be 6 what were we using? 6.63 times 10 to the minus 34. That's Planck's constant, divided by its momentum, which is just 5 times 10. I mean, can you guys just, how small is that going to be, right? You're dividing 6.63 times 10 to the minus 34. You're hardly even changing that number. You're like 1.3 times 10 to the minus 35 meters. So if you recall our condition for diffraction, that the ratio of the wavelength to the width of the gap that you're shooting it through, or like the slit, had to be greater than or equal to 1. Well, like if you wanted to observe diffraction of a bowling ball rolling at 10 meters per second, you'd have to be rolling your bowling ball through an opening that was 1.3 times 10 to the minus 35 meters. So why do we not notice wave-like properties for everyday objects and larger particles? Well, it's because their de Broglie wavelengths are so small that we don't notice them. For reasoning, so we for back in our first lesson on waves with diffraction, this wavelength is too small to be noticed. But for things like an electron, now electron moving at a certain speed, its de Broglie wavelength is not that small. It's small, but I mean, it's large enough that if we shone an electron beam through a double slit apparatus like we've done earlier, that you would observe some diffraction of electrons. That's pretty cool. All right, so as I kind of teased, de Broglie's formula was confirmed later when electrons were observed to diffract. And again, for great visuals on that, check out the just interesting videos I have posted today. Passing electrons through a thin metal sheet produced the interference patterns that light showed. So it's like a particle version of the double slit experiment. So your practice with de Broglie is just finding the de Broglie wavelength for, just getting a bit of practice using the equation, finding the de Broglie wavelength for bigger particles, smaller particles. But again, the big idea there is why we don't see diffraction of larger particles is because their de Broglie wavelengths are too small compared to the slits or openings that we might be encountering in our everyday life. All right, guys, so what topic is next? Well, there are no more topics, at least with me. We're actually done the course. So I just want to take this time to say that I've really enjoyed shooting the content for the course. We have left nothing out. We have covered everything, maybe not in as much detail as you would like or I would like, but we covered in terms of the physics spectrum. We talked about a lot of stuff. So that was a really cool 3 or 4 weeks of making content. So for the people taking my course right now in summer school, at this point, your next steps are, obviously reviewing and finishing up this unit, but just getting ready for your exam, finishing your performance task. We're done. So this is the last time I'll be signing off for a video of content for this summer. So it feels good, man. Guys, stay well. Have a great day, and we'll see you soon.